Right, so literally carrying on from where we left off before. Repeated linear factors. I was at this stage where I'm trying to eliminate to find A, B, and C. Remember, I had to make the denominator split on each one because it's repeated linear factors. So I'm repeating this factor with the power of 1, repeating this factor to the power of 2 until I end up with this order, and then I put on whatever's left. So I've said let x equal -1 to eliminate this one here and this one here. So if I put this in on the left hand side, that's minus 1 squared minus 10 times -1 minus 5 is the same as, well, the A disappears and C disappears, and I get B -1 minus 1. So -1 minus 1 would be minus 2b, and on the left hand side minus 1 squared would be -1. Plus 10 is 9, minus 5 is 4. So therefore B must equal -2. And again, let x equal, this time 1, to get rid of this and this, to isolate C. So this is -1 squared minus 10 times 1 minus 5 is the same as the A's and B's disappear, and I'm left with C. 1 plus 1 squared. So this gives me -1 minus 10 is -11, minus 5 is -16. It's the same as 4C, because that's 2 squared. So therefore C must equal -4. But this time, I haven't got anything left, have I, to let x equal to reduce all this stuff to 0. So what I can do is, I can let x equal anything else, and then I can use my previous results, B and C, to find A. So the most obvious thing to use is to let x equal 0, because it makes so little, much less calculation for me. So on the left hand side, minus 0 squared minus 10 times 0 minus 5 is the same as A times 0 plus 1, so 1, 0 minus 1 minus 1, plus B, 0 minus 1 is -1, plus C, 0 plus 1 squared. So this gives me -5 is the same as -A minus B plus C. I know that B and C are -4 and -2 and -4. So I get -5 equals -A minus -2 is +2 and -4. So this gives me -5 is -A -2, and if I put that all together, I get A equals, that comes over 3. Yeah? So now, again, not finished. I need to write my starting equation. X plus 1 all squared, x minus 1. That's the same as 3 over x plus 1. B is -2, so -2 over x plus 1 all squared. And then C is -4, so -4 over x minus 1. And then we're done. So this time we've got the same thing, except on the denominator, I don't have it split up into partial fractions. So I don't know, into linear factors. So I don't know what it's composed of. Are there repeated ones, or what is it? So always a good idea to try and factorize that bottom. So I get 2x squared plus 2x minus 18 over, well, x is the same, so x squared minus 6x plus 9, which would give me 2x squared plus 2x minus 18 over x, and this thing here can be factorized into x minus 3 all squared. Right, so actually I've got a repeated linear factor case, so I have A over x plus B over x minus 3 plus C over x minus 3 all squared. Okay? And then it would be the same as normal, so I can say that 2x squared plus 2x minus 18 is the same as a, well, what's missing from the denominator from a? Well, it's x minus 3 squared. Plus b, what's missing from that? Well, it's x, and it's x minus 3. What's missing from c? Well, it's just x, isn't it? You see? And then again, I can let my x equal things, and I can figure it out from there, as in the previous example. So maybe have a go at finishing that. What I'm looking at now is the case of improper fractions. So if I'm looking at the case of improper fractions, what I'm talking about is if the denominator, the highest order of the denominator, is the same as or more than the order of the denominator. So let's make that clear. So if this order in the numerator is greater than or equal to the highest order of the denominator, then it's classed as an improper fraction. So to test that, I need to multiply these out to make sure. So I get 3x squared minus 3x minus 2 times x squared minus 3x plus 2. Right, so the denominator and numerator have the same highest order of x, which means I have an improper fraction, which means I must perform algebraic long division first, okay? Because I know this is going to give me the form of just a constant, I need to find what that is, plus b over some linear factor plus c over some linear factor, okay? So let's do the algebraic long division then. So I'm dividing 3x squared minus 3x minus 2 by x squared minus 3x plus 2. So how many x squareds and 3x squared? Well, there's 3 of them. Minus bracket times out this thing by this. So I get 3x squared minus 9x plus 6. Draw a line, minus them out. 3x squared minus 3x squared is 0. It's the whole point of what I'm doing. Minus 3x minus minus 9x is 6x. So minus 2 minus 6 is minus 8. So actually my remainder is this 6x minus 8. So I can say now that this thing is equal to, well, a must be 3 plus 6x minus 8 over my original x minus 1, x minus 2, which would give me 3 plus, let's call that b then, over x minus 1 plus c over x minus 2. And actually what I'm doing now, this bit's done. I need to compare this bit with this bit. This is where the partial fractions come in, yeah? So you can take this bit to the side, but don't forget about it. So actually I've got 6x minus 8 over x minus 1, x minus 2 is the same as b over x minus 1 plus c, over x minus 2. Then we're just like we were in the first case with just linear factors. So I can say 6x minus 8 is the same as b x minus 2 plus c x minus 1. Let x equal 2 implies 12 minus 8 is the same as b disappears. 2 minus 1 is 1, so c, so therefore c equals 4, and let x equal 1 this time. So I get 6 minus 8 is minus 2 is the same as 1 minus 2 minus b implies b equals 2. So my final answer, 3x squared 3x squared minus 3x minus 2 over x minus 1 x minus 2 is actually the same as 3 plus 2, because b is 2, over x minus 1, and c is 4 plus 4 over x minus 2. And again, what I can do with that is, well, I can integrate it, for instance. So let's integrate it. If I integrated both sides, with respect to x, all the individual elements integrated, yeah? I get this thing is the same as 3x plus 2 mod log x minus 1 plus 4 mod log x minus 2 plus our constant c. So I could do that, or, you know, maybe the question will say, find the binomial expansion of this thing. So how about I find the binomial expansion, so we'll forget this one up here, and we'll move this thing over, so move this answer over. Into here, right, and I'll rub that out, so that was a 3, and that was that, get rid of the dx, so that was a 3, wasn't it, and that was a plus 2 over x minus 1, and that was a plus 4 over x minus 2. Now if it said find the binomial expansion of the whole thing, fine. Because what I'd have is, I need an expansion for this one. So this is the same as 3 plus 2 x minus 1 to the power minus 1. But remember, I need it in terms of 1 plus x. So this is 2. If I take out the minus 1, on this is 2 times minus 1 to the power minus 1 of 1 minus x to the power minus 1. Yeah? And the same again on the other one, I've got plus 4. I need to take out a factor of minus 1 to the minus 1, and I get 2 minus x, but I still haven't got a 1, so I need to take the 2 out as well. So this is 3 minus 2, 1 minus x to the minus 1, minus 4, and then take out the 2, so minus 4, take out the 2 to the minus 1, and I get 1 minus a half x to the minus 1, right? So this is 3 minus 2, 1 minus x to the minus 1, minus 2, because 4 over 2, 1 minus a half x to the minus 1, yeah? And then what I would do is, I would just use my C4 binomial expansion. So I'd expand this, I'd expand this, and I'd expand this. So if we expand that one, for instance, just to show, this is the same as, if we're just doing this part, 2, then we've got 1 plus our nx, so this time our n is minus 1, our x is minus x, plus our n minus 1, our x divided by 2 factorial, and let's say the question asked up to the term x cubed, minus 3 factorial, minus x cubed, plus dot 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 dot. Yeah? So that would be that one, and then call that 1. And then we'd have number 2, I've got a 2 on the outside again, and I'd have 1 plus, well, my n is minus 1, my x minus a half x, plus minus 1 minus 2 minus a half x all squared divided by 2 factorial, plus minus 1 minus 2 minus 3 over 3 factorial, minus 1 over 2x cubed, plus dot dot dot. You get the point, yeah? So I can do a lot with my partial fraction knowledge. I can expand stuff out, I can integrate it easily, I could differentiate it more easier as well, because I wouldn't have to use this horrible quotient rule. Actually, I could bring it up and I can use the chain rule. So, there we go. That's it for partial fractions.